Okay, so before we get started on actually installing, you should know about some requirements. You need to have, for Windows, you need to have Java JRE. The latest is updated would be good. For Mac OS, you need the Java JDK 8. That's not the latest one, so just be careful about that. If you start the installer, it's going to warn you about this anyway, so it will check to see if you have JDK 8 on Mac and JRE on Windows. You also need Python. This will be installed automatically if you don't have it, or if you don't know what it is and don't use it very much, then it will ask you it will ask you if you want to install Python. It does take some time, so you might want to start it as soon as we get, going, and it takes a bit of space as well, about 1.5 gigs or so. I'm not exactly sure, but so it takes a little while to download it. We may find that if you're downloading it during the talk, then you might cut out. So we'll see. So first thing is you can go to the website here, github.com/software/corvus/releases/latest, and I will post that in the chat. To everyone, so you can have it. And this will always give you the latest release, so that you can have that. So then on that website, there is source code. There are installers for Mac and Windows. And again, if you don't really use Python, or if you use Anaconda Python or Miniconda, then I would go ahead and use the installers. That makes everything really easy. It will install JFEFF and FEFF10 for you, and then it will also install basically everything you need except for Java. But if you use Python on your own for various projects, I don't suggest you do this. It might, mess up your Python environment. So you should instead download the installation instructions and install it as they specify. There is a little bit of warning that I don't know that it will work right away, because some things require extra downloads of various tools. So for example, in Microsoft, you need the Visual Basic C++ build tools, and in Mac OS, you need the Xcode developer tools. Or if you use Linux, again, also you'll want to look at the installation instructions. And if you do need help, you can email me, and I'm sure we can get it working. I've installed it on all these machines before, or all these OSs before. The other thing that you need to do if you're going to install FEFF10, and again, the installer will download and run the FEFF10 installer as well. It's going to ask you for a password. So you need to register, and that I can also throw into the chat, the registration window in case, but it will tell you, it will ask you if you want to register, and then it will give you a confirmation email after you register, and it'll give you a password and whatnot. So let me just put that in there as well. And this isn't for, we're not charging for FEFF10, it's open source, but we'd like to know how many people are actually using it. And then also, allow us to give you some news about updates, workshop opportunities. And we may, actually, I'm planning on starting a forum for Time Software generally, where people can ask questions and have feature requests and bug notifications and things like that. Okay, so let me go back to, it's not, oh, there we go. Okay. All right. So then once you actually download the installer, on Windows, you just need to download it and install it as usual. It will, Windows 10 will ask you whether you really want to keep it as you download it. And then it's going to ask you again whether you want to keep it. And then when you actually run it, it will ask you whether you really want to run it. And you always have to kind of find how to run it because it's not signed. But just, follow the instructions after it starts running and carefully, and everything should be okay. On Mac OS, you do things a little bit differently. You want to download the installer, open a terminal, and then type these commands in there. And all of this, in case you missed this, all of this is on the instructions that you can download from the page as well. And I can show you. If you look at the releases, it has the installation instructions here in PDF form. So that's all okay. So then once you're done with that, you can find JFEF again under the start menu here, or I think it should also be on the desktop as an icon. In Mac, it's in a slightly different place. It will be in your home directory called jfeff.app, and you can open it in a couple different ways. You can start a terminal and type open jfeff.app, open space jfeff.app, or you can just go to your home directory and double click on jfeff.app and that will open it. So again, it pops up a window here asking about moving files. You want to click no on that. And then the next thing you need to do is get your settings right here. It doesn't point to the correct place when you first start it. So you want to, again, click on the settings down here. And next to FEFF module dir, you click browse. And then on Windows, you're going to go to the place you installed it. If you installed for everybody, that's in program files. So I'm going to go up to C, and then program files x86. You'll see JFEFF, FEFF10, FEFF10, and bin. And again, if you miss this, it's on the instructions. And similarly for the Mac OS users, it's on those the PDF instructions, what you should do, what the path is that you should do. Okay, so you can hit OK. And then just to test, you can hit save and run. And that will run the copper XFs. I think it's L-Edge XFs. And it's very fast. This particular spectrum, it's just XF, so it's not difficult to calculate in terms of speed. And then you can plot it just to see what it looks like. This is a little bit hard to see, so you can click on the little color, and you see there's a spectrum. Okay, that's good. So just a quick intro on how the GUI works, or how it's organized. We've got a couple different panels here. One has all the information about the structure and the material. So, and I'll show you what these things do in a minute. But you can view, or actually we'll talk about it now. You can view the molecule. You can go here and click view, for example, and you can see this is a cluster of copper atoms. And you can edit atoms, and it shows you what the structure is. This is XYZ, And then it shows some potentials here, and I'll talk about those later. There's also a panel that has to do with spectrum settings. You can see it's set to XAFs here, but there are all sorts of spectra under this drop-down menu. And as you change the spectra, then some of these options change as well. And then there's a control dashboard where you can choose which executables run. And these sort of some of these are self-explanatory. The first part is to calculate the potentials, self-consistent potentials maybe, and so on. And it's important to be able to turn off some of these modules, because sometimes you just want to calculate something with slightly different broadening or with a Fermi level shift. And it's very fast to do that if you only run this last cross sections part. And then finally, you have the module options dashboard, which has options for each of these different modules that you see in the control dashboard. And there are a lot of them. And so, you might not be sure exactly what they are. So you might want to know how to get documentation for this. And one way is through the JFEFF app. You can click on help and it pulls up this screen, and you can just hover over different things and it will tell you what they are. So that's a good way to just kind of investigate different things. You can, of course, also look at the manual, and the manual is located in the same directory that JFEFF is in. So a good way to get there is to go through the start menu, for example, right click. You can open file location and then do that one more time. So now here's the FEFF10 user guide. So you can open that, take a look. It has lots of information about FEFF10 and some examples and things like that. Okay, so we can open and run another example. This one takes a little bit of time to actually run, but we can just let it run as we go. So what you'll do is open, and then this should take you to, well, it takes me to documents. So I'm going to actually go home. You want to go to your user directory. You may not have that in your desktop, but anyway, see users and then your user. So that's your home directory. And then there should be a directory named FEFF10_examples. And you can see there are lots of different examples in here. And I'm going to go to Zanes and boron nitride. And we can open this FEFF.imp. And this is this being a Zanes calculation. Now things have changed here, you can see. It now has slightly different parameters up here. And as well, instead of having a path length, or let's go back to XAFs for a second. RPath is what we call this, which is the maximum path length you can do for XAFs calculations. It has FMS, which, if you remember from John's talk, full multiple scattering has to do with the matrix inversion to calculate the Green's function rather than an expansion to calculate the Green's function. So anyway, you can go ahead and click save and run on this as well. And that will start, but will take a while. So I'll just continue here. And we can think about what's in the output. Let me see, is this right? Yeah, okay. Just talk about different files that you'll find here. There's one called xmu.dat. That's the main output of Zane's calculations. And that has the spectrum it has a header with a lot of different information, like the Fermi level, the core hole broadening, a variety of other things. It also has the atomic background and the fine structure, so the chi versus energy, and also has a different energy or different x-axes. So for example, it has energy and K and various things like that. As John showed before, there's a lot of correspondence between the angular momentum projected density of states and zanes. And so you also have output. If you ask for LDOS, then it will give you output in LDOS NN.dat, which gives you the projected DOS for the local DOS for the potential type NN, which I'll describe later. Similarly, you have log files that you might look at if something happens, and then potentials, which normally people don't need, but if you ask for these potentials, then you can plot them and see what they look like and things like that. Okay, so this is running. It's going to take a little while. Looks like it ran through the LDOS. So we'll have the LDOS. It's almost done, actually. So I'll just wait for it for a minute, and then we'll talk about how you build an input file. And in fact, actually, what we're going to do is open the input file for this one just so that we can see what it looks like. So I'm going to go to my user and Corvus, FEFF10 examples. There it is. And Zanes, boron nitride. And then I'm going to open FEFF.inp. And I'm just going to open it with Notepad. That should work fine. And we can just kind of look at what this thing looks like and what is required in a FEFF input file. So FEFF, generally, the main thing that it requires is the structure of the system. So atomic types or atomic species and coordinates. You do have to set up, how you're going to deal with the potentials. So the way FEFF generally works, again, is you give it even if you're doing a solid, for example, you give it a large real space cluster. It does have a k-space method, but in many cases, you give it this large cluster and you calculate the absorption for one atom near the center of the cluster, and that simulates the X-ray absorption for a solid. And then you give it potentials, a unique potential for each of the unique atoms in the system, but you treat the cluster as if it were in a solid. So you treat nitrogens all the same, even though some of them are near the edge of the cluster. We're not trying to simulate that here. So, and then you treat all of the borons the same as well in this system, except for the absorbing atom, which is different because it's going to have a core hole in it. And just to show you where that shows up in the JFEFF GUI, again, you can hit edit here and you can see there's this IPOT 0, that's the potential label, and that's the absorbing atom. So this is the boron edge. And then you have one potential for all of the other borons and one potential for all of the nitrogens. And similarly, you have the same kind of structure down here as you see in the input file. So obviously, it's not ideal to have to build these input files by hand. So there are various tools for obtaining these. So I'll talk about that next. Now that this is finished, for me, I can go ahead and plot it. And there it is. This is the boron K edge. And you could compare with the density of states, since we also calculated that. So we can open. If we do 0, 0, that's the absorbing atom. So that's going to look a lot like the Zanes as long as I choose the correct column to plot. So let's show this. And xmu.dat, what I need to do is change the column on this in the domain to 2. And then the LDOS, right now it's plotting columns 1 and 4. And the way this actually has the density of states in there, you've got energy in column 1 relative to, of the photoelectron relative to vacuum. And that's the same energy scale as column 2 in xmu.dat, but you can't really see the number there. But but the next columns are S, then P, then D. So column 4 is actually D. This is K edge. So dipole selection rules say that this should look like the P density of states. So I want 3 here. And I'm going to change the color because it's pretty hard to see. Now, it's not calculated very high in energy, but you can see that there are corresponding peaks here at 5 eV and at negative 2.5 eV or so. So this looks quite a bit like the Zanes so far. Now, you can change the energy scale on this if you wanted to calculate LDOS out further. This is listed right here. It goes from -20 to 10, and that is relative to the Fermi level. No, sorry, that's relative to the column 2, which is just relative to vacuum. So you can see it goes from -20 to 10. So if you wanted to go a little bit further, you'd go to 30 or something and recalculate. But you don't really need to do that right now, or I don't really need to do that right now. So I'm going to close the plot here. Let's go back to PowerPoint. Okay, so how do we actually build these FEFF input files, especially when we start with some structure file like an XYZ or a CIF file, something like that? One way to do that is to go to Web Atoms, or you can actually use Atoms. It also comes with the Athena and Artemis or Demeter XAFS analysis package. So I'm going to go to this and show you what it looks like. So this here, you can browse and select a CIF file, crystallographic information file, and then once that uploads, then you can choose various options to create a FEFF input file, and we'll come back to that. Okay, so that's one way to get translate CIF to FEFF input file. And then, Corvus also has translation from basically XYZ or CIF formats to FEFF, and we'll talk about that later when I give a demo on Corvus. So where do you actually get these structures? There are lots of databases, experimental databases for crystallography, as well as other formats of structures like XYZ, or sometimes they're in what people call the ZMAT. And one good way to transform to XYZ, if you need to do that, is through I think it's Open Babel. It's one code that does that. But anyway, there are lots of places to get crystallography, at least CIF files. And then you can also get them from theoretical databases. So for example, the Materials Genome Project has lots of different materials calculated using VASP, where they've calculated the lattice constants and things like that in the structure using VASP. And then also the computational chemistry comparison and benchmark database, which is more for molecules. I think that's a mixture of experimental and theoretical structures as well. So we could do, an example. So let's go ahead and I'll go to the American Mineralogist database. And I already have this set here to search for manganese and oxygen with the exclusion of everything else. So let's go look and see if we can find the right one. That looks right. Okay, so we can look at this view. This is manganese oxide, MnO. So let's go ahead and download that CIF file. And I'm just going to view to see what file it is. Okay, I already had it named that, but now I can go and upload that to here. You should be able to also just post the URL here. Okay, downloads there. So I can open this and submit crystal data. And you can see it put everything in here. We've got manganese oxide, and it created a FEFF input file. And you can download this FEFF input file, but I personally tend to just copy it because sometimes it downloads with the wrong line endings, comparison to Linux, Mac, or Windows. So I just copy it, and we can throw this into a file in some temporary file and just put it here. Make a new directory, because when we run this with FEFF, it's going to have a lot of output. So make a new directory and then a new text file. And we're going to have to change this. So paste it in here. And actually, I'm going to save this as, oops. And I want to do all files here. And you have to save it as feff.inp. We'll save that. Okay. So now we can see we have a feff.inp file in there. And we can open that with JFEFF. And you okay, so it's set up to run XAFs, but you could change that if you wanted to Zanes, for example, and put in, say, 5 for the FMS radius. Similarly, there are a variety of things here that are set to do XAFs. For example, self-consistent potentials are not selected. And that actually comes from the fact that in the web atoms, I chose the potential style to be FEFF6, which is only XAFs. So if you wanted to do something more like Zanes at least, then you could do FEFF8 and run it that way. that will give you an input file that's closer to where you want to be if you're running Zanes. But I'll just go ahead and run it like this and put 10 here for decay max. That's what this field is. And then SCF, the first box here is RFMS. You can actually hover over and see what that is. That's the radius. So I'm just going to put something small so that it doesn't take too long. And then I'll just hit save and run. Okay, so that's going to take a little bit of time, but we can again view the cluster. So let me see where that went. It's still calculating. It should be done not too long. It's calculating FMS here. You can see a variety of information here as well. Going by, some of it has to do with charge transfer, for example. In the SCF iterations, you can see the Fermi level changing, and then at the very end, you can see the charges on each atom for each angular momentum L. So this is the absorbing atom, and then you have angular momentum 0 or S states, and these are only the valence charges. And then at the very end, you have the charge transfer. Okay, so that's done. And again, you can plot that. And there it is. Okay. So it's definitely very useful to have this web atoms to translate. Now I'm gonna go back to the slideshow here. So we could also do a slightly more complicated example, which would be manganese Mn2O3, where it's not really any harder to build a FEFF input file, and we'll do that. But it is a little bit more difficult to deal with calculating the Zanes of the entire system because there are multiple unique manganese sites in this system. And there are also multiple unique oxygen sites. And so how do we deal with that within web atoms? Let's go back and look at let's get Mn2O3 here. That's this one here. Oh, that's Mn3O4. Well, let's see, there's I think I already have this one downloaded actually, so I can just load it. Okay, so I'm gonna go ahead and load it, but you can find Mn2O3 or you can do Mn3O4. That has lots of different sites as well, and load that into web atoms. So here you can see this isn't that still isn't the right one. Okay, so let me get the right one here. So here you can see this has 2 different manganese sites and 3 different oxygen sites. And if you want to differentiate these in terms of the potentials, which is not a bad idea since there aren't that many sites here. In some cases, if there are 100 different sites in the unit cell, you don't really want to differentiate between every single one of them. FEFF will have some trouble with that in the self-consistency loop. But here you can do FEFF8 sites, and that will give each site its own unique potential plus the one absorbing atom potential. And you can view that over here, looking at the potentials. You can see there are 2 different potentials for the manganese and 3 different potentials for the oxygen plus the absorbing atom. So we can go ahead and copy that. And create a new directory. I've got one here. Get rid of all this. And a new, well, I guess we just could open. And then again, save this as feff.inp. And we can run that one. So I'll open a new one. I'm at 203. Okay, we've got this, and we can view it as well. This is an extremely small cluster. It's probably not large enough. That's something you can also control how many atoms come out of web atoms by changing the cluster size. So you might change that to something fairly large. It doesn't really change the size of the calculation to change the cluster size, as long as you keep the SCF and FMS radii the same. So it's not a bad idea to just have this fairly large, 10 angstroms or something like that, rather than 5 or 4.5 that they have there. So I'm going to change this again to Zanes and fill these in with Kmax as 10 again and FMS as 5 like I had it before, and 3 for SCF. And we can hit save and run this. And that will take a little bit of time. I'm not going to go through all of this. I'll let people go through it on their own. But the main thing to note here is that if you edit this and look at the different, the structure of this file of the manganese oxide system, you're going to have different Zanes from the manganese with potential 1 than you will from the manganese from potential 2. And so you're going to need to change the absorbing atom from one of these to the other. So this is an Mn2 plus, right? And you want to change that to an Mn3 plus. So you can change the potential here, and you want to get rid of you want to make the Mn3 plus the absorber, so you can change that to 0, whichever one, one of the closest ones to the center. These are all at the same, well, I guess we could go to the, Hang on. Let's put that back to 2. This is another reason why you want a larger cluster than this particular cluster probably. But we can change that to 0. That denotes that this atom here is now the absorbing atom, and we have to get rid of this 0 and put that as the same as all the other Mn2+, which are a potential 1. So we could put potential 1 here. And then we would want to save this file somewhere in a new directory. So it's like the second absorber of the cell. So for example, you could do save as, and unfortunately this puts me in the same. Okay. Mn203 here. And maybe we want to make a new folder here. So we can click there, site 2. Oh, I don't know if it's saved in the right place, but anyway, I'll let you go ahead and run those and compare the two. The Zanes should look fairly different. But once you're done with that, then you have 2 different X-ray absorption spectra, one from each site, and you'll have to use something different to average those. And you have to average them with the correct stoichiometry that comes from their site symmetry. And in particular, the second manganese site, which is the Mn3+, is twice as prevalent as the first one.